This video is an introduction to algorithmic problem solving. Before we can really start solving problems, I'd like to define what a problem is first. According to the dictionary, a problem is something difficult to deal with. That makes a lot of sense, doesn't it? A definition of a problem has three main parts. The three main parts are the initial conditions, what the state of the world is when the problem solution has to begin, the goals of the problem, what we hope to solve as we go through the problem, as we finish the problem, and three, the barriers that stand in the way of us finding a solution or reaching those goals. If a problem didn't have barriers, it wouldn't be much of a problem, would it? The other term I would like to define in this introduction is an algorithm. An algorithm, again according to the dictionary, is a set of steps that are followed in order to solve a problem. You can think of a mathematical expression as an algorithm for solving a problem. You can think of computer programs as an algorithm. You can think of a recipe like you have in the kitchen to make bread or make a cake as an algorithm, or assembly instructions or other algorithms. Stop and think for a moment of some of the other algorithms you know of in your life and use. Bransford, in his book The Ideal Problem Solver, created a 5-step methodology, or another algorithm, for solving problems. He called it the ideal method. Each of the letters of ideal stand for a word. I, identify, D, define, E, explore, A, act, and L, look. In the next few slides, we will go through each of those and discuss what they mean and try to figure out how best to apply them in our problem solving. This diagram shows how I like to think about the ideal method. I don't think about it as a waterfall method where we go step, 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 but more of a circular problem, more of a circular kind of thing where we move from identify to define to explore. But sometimes while we're exploring, we might find something that we missed or something that we need to explore further. We may need to go back to identify, or we may need to go back to define more of that. So I think of it more as a circular problem solving method with shortcuts to go back to the previous steps. So if we find that we've missed something, we can always jump back. Identify. What does identify in the ideal method really mean? Well, we need to get a complete understanding of the problem. What are the initial conditions? What data or input will we be given as we solve the problem? What should a solution include? And maybe what it shouldn't include. We're not trying to come up with solutions at this point. We're just trying to come up with a good understanding of what a good solution or what the problem is. We need to understand the problem long before we can finish it. There are a series of questions that we should ask ourselves to make sure that we fully identified the problem. In the problem statement, do I understand each and every word and why it's there? If there's a word I don't know why it's there, an and or an or anything, I need to figure out why that word is in the problem definition. What's the domain of the problem? Is this an engineering problem, a medicine problem, a business problem, a computer science problem? What domain is this problem, and what kind of experts might I need to bring in to help solve this problem? Can I diagram the problem or write the problem out in my very own words, not somebody else's words? What other problems are related to this problem or may happen as we solve this problem? Because lots of problems create other problems. And have I ever seen a problem like this, and do I already have a good solution for that problem? Well, because if I do, then I don't have to do a whole lot of work to complete and solve this problem. The second major step is called define. When we define a problem, we need to figure out and define a way that we can actually act upon. We're still not trying to find the solution here. We're just defining the problem. We need to formally define the problem in a step-by-step full description of what the problem is. We need to answer all kinds of questions, and we need to figure out what questions need to be answered about the problem. And we need to define every little small part of the problem. We need to fully define the problem and take it down to its smallest chunks of understanding. As we're defining the problem, we really need to ask ourselves the following questions. Have we defined the initial conditions, the inputs, the calculations, the outputs, and the final condition? And it's not just do we know what they are? What is the definition of each of those parts? Can we break this problem up into a group of smaller problems? That would be an important thing to know as we define the problem. What constraints, monetary, technological, and others, and barriers stand in our way of solving this problem? And then, what are the existing algorithms to solve problems or parts of the problem? Because if there's an algorithm that we know or have used that will solve part of the problem, then that makes defining and understanding the problem that much easier. The third phase is to explore the problem. Now that we've defined the problem, now that we've identified the problem, it's time to explore various strategies to actually solve it. Develop several different ways to solve the problem. Strategies, methods, algorithms. There might be several different solutions. We need to we need to explore them all, and then we need to choose a good one. It may not be the perfect solution, it may not be the best solution, it just has to be a good one. And good can be defined in time, in money, in complexity. There are all kinds of different ways to define what a good one is. And that's why good was left kind of generic in this discussion. In our exploration of the problem, the questions we need to ask ourselves to make sure that we fully explored solutions. Can we solve this problem on paper? Can we describe our solution in detail, in English, in sentences, in pseudocode, in flowcharts, all kinds of ways? Do we understand what data will be needed and how we're going to store the data? That's a really important thing to have explored at this point and to understand exactly what we're going to do. And then we need to know how we're going to apply sequence, selection, iteration, or all three in combination. In computer science, sequence is the process of going step by step by step by step in order. Selection is the process of asking, well, if this happens, we do this, or we do that. If this happens, we do this, or we do that. And iteration is the process of repeating ourselves over and over again, usually using selection to say, are we done yet? No. Are we done yet? No. Are we done yet? Yeah, we're done yet. So we will often implement and combine all three, sequence, selection, iteration, in our problem solution. The fourth step in solving a problem is to act. And at this point, we fully explored the problem. We understand the problem, and it's now time to solve it. We formally write our program or our instructions, or we build something, or we implement our solution, our good solution from the explore phase. As we're acting on our problem, do we fully understand our models? Can we write the code? Is it efficient? Have we tested it? Does it really work? Is it efficient? Is it understandable? And does it translate from the exploration that we've done into an actual actionable solution? Act. And the fifth part of the Branford ideal model is to look. The problem has been solved. We need to look back. We need to be reflective and learn lessons about how to solve problems better in the future. So we want to look at the problem, at the process of solving a problem, not necessarily our solution, but how we came upon the solution. And sometimes we want to look at the solution too and try to figure out ways to do it better in the future. Some people call this closing the loop, to make sure that we're always in continual improvement. Some of the questions that we can ask ourselves in the look phase is, can I actually program this algorithm using the tools at my disposal? Are there existing models that I can use to more easily and reliably implement this in the future? Can I test the code with real world cases? Does it work? Is it completely working? Is the user satisfied with how we solved the problem? And in an environment that's always changing, like business and industry, will the algorithm require updates and changes for it to continue to work? We always have to look at our solutions. In conclusion, the ideal method is not the only way to solve a problem. It's just one that I really like. Your company or your client may have a different problem-solving methodology they like to use, but if you look at all of them, they'll all be very similar to ideal, but they may call things differently. One just bit of advice is have a formal structure to help you make sure that you don't miss anything that's important. A checklist, some kind of process, and the more formal the better, because that way you won't miss things. This slide includes works cited and used in the presentation or the preparation of this material. I thank you for watching.